cyber-cni, cybersecurity for critical network infrastructures.
Cybersecurity is an amazing topic to study, and particularly it's an arms race between us and the attackers.
Building systems resilient to cyber attacks is of course a challenge of great practical interest.
Every day there's a new challenge to face.
Strong mathematics, but also a practical point of view. You need both.
Help giving users a more secure experience.
It's like a game because you have two sides, the defender and the attacker.
It is a wide domain. We often necessitate knowledge from other areas, in my case industrial system and machine learning.
The domain is complex and it requires the understanding of heterogeneous data sources and use cases.
And new things to learn.
So cybersecurity is very motivating for me because in cybersecurity you may have some prior knowledge on the nominal behavior of your system, but you have to face attacks that are yet unknown.
Welcome to the Chaire cyber-cni, cybersecurity for critical networked infrastructures. My name is Marc-Oliver Pahl. I'm the chair holder and I cordially welcome you to the virtual lab tour. I will tell you a bit about the topics we're doing research on. I will tell you about the people at the Chaire, and I will tell you about the equipment that we have at the Chaire to do our research. But let's start with the first things first. Critical networked infrastructures. What is this? I brought you some examples here. So you see healthcare, water supply, energy supply, communication, data centers, Industry 4.0. You see traffic, you see defense and national security, you see finance, education, research, innovation, food, and many more applications. So networked systems are part of our everyday activities. You will barely find activities that are not controlled by computers and algorithms in the background. And nowadays these controllers are interconnected, and they are not only interconnected locally, but they're interconnected to the big internet. And in the big internet you do not only have good people like you and me, but you also have attackers, so people with bad intentions that want to attack the systems that we see here. And when they run their attacks, they do not only attack the systems, but they attack our entire society, because the infrastructures we especially look at are called critical, as they are essential for our society to work. So imagine, for instance, that your water supply is not working anymore, or any of the things I mentioned here that are critical for our society. So we see it's important to protect these infrastructures, the networked infrastructures, and this is exactly what we do at the Chaire. I structure you what we do in the research into three areas. Let's start with the first one, which is prevent. Here a keyword is security by design. In this direction we want to make systems as secure as possible. For that we use existing mechanisms, combine them for the complex installations that we look at, or we develop new mechanisms. And the result is that we have secured systems that implement all the security that is possible to implement there, and by design, meaning that it's really deep rooted in the system and attackers cannot circumvent it. Now you may say, okay, when you have security by design, what else do you need? Can't we stop here? And the answer is we cannot, because the systems we are looking at, they are not static, they are dynamic. And that means you're adding components, you're removing them, and the systems are interacting with their environment. For instance, think about a conveyor belt and the product is falling down. Process has to interact with that, or human intervention. with the processes. And when you make systems secure by design here, then you somehow cage them. So you say, okay, you system, you can only do this and that because this is according to my security policy, and you cannot cage them entirely because then the system cannot operate anymore. Therefore, you have to give the system some space for it to operate, and through this space also attacks can come in. Therefore, we need more, and this is exactly what we do in the second part. We do detect. So here we do continuous monitoring, so we look at what is the system doing, and we investigate if it's still what we expect the system to do. And if it's not what we expect the system to do, then it's a so-called anomaly. So something that is anomalous according to the purpose of the entity. The entity might be software or hardware. And when we detect now an anomaly, we do not stop, but we also develop algorithms to automatically defend against that by, for instance, isolating parts of the system or changing configurations and other things. So this is one thing we do for the mitigation. The goal is to have resilient systems, meaning that even when there are attacks, the systems recover automatically and maintain their core operations. And a second thing that we do here also is bringing the human in the loop, because the systems we secure are not isolated from the world. They are embedded in the context of a company, of a society, and these give the rules that the systems should implement. So we develop technology that implements the rules that the humans give, and as the systems are complex, the interface is also crucial for securing a system, and therefore we look at mixed reality interfaces, which is something innovative, where you have, for instance, glasses and you look around, and then you can suddenly see in the ambience what is happening there that is security relevant. So you can see who talks to whom, you can see where are some problems and so on. And so this gives you a more intuitive understanding of what is happening, and it gives you also a more intuitive access to the configuration of the systems. So now you know a little bit the high-level areas we're working on. For that research, we use lots of methodologies. At the bottom here, I put you some of the currently hot topics in research. Of course, we also use machine learning. We use it, for instance, here for doing anomaly detection, because machine learning allows us fuzzy analysis, meaning that we can analyze data that we have not seen before and still get good results. And we use it, of course, also here for the defense mechanism, because then we can develop defense mechanisms that are adaptive to how the system behaves. On top of machine learning, or in addition to it, we also use another very important concept, which is the so-called digital twin. So this is like when you have me here physically, and you put a software copy on me next to me, and this one you can use for multiple things. You can use it for the anomaly detection, for instance, but you can also use it to emulate what happens when you change system configurations. You can use it for emulating attacks and so on. So it's a very important tool that we use in almost everything that we do. The next point I put you here are so-called distributed ledgers. You know them from the blockchain, for instance. That is the backbone of the Bitcoin cryptocurrency that you see here. Blockchain or distributed ledgers can be used to exchange information between untrusted parties, and this is something that comes in handy when we do federated things like federated detection or federated reconfigurations, for instance. So this is where the distributed ledgers come in. The last point I want to mention is ethical algorithms. So what do I mean with that? As we develop autonomous behavior, as we develop behavior of software systems that interact with humans, we always have to take care of the component interaction algorithm human, not to develop something against our society. The example is when someone asks you to develop a mass surveillance tool, it's your responsibility not to do it, because it would be against our society, similar to developing a bomb. And with the ethical algorithms, we look at that for everything we do, following what Martin Hellman always says, the Turing Award winner: practice the ethical decisions in everything you do, because then when a big one comes, like you are asked to develop a bomb, you can more easily take the decision of saying, no, I won't do it. Okay, so now you know a bit what we're doing in the big picture. Let's get more into the details. So behind me you see the current topics that we are doing research on. Let's start at the top here. So we use autoencoders to look at signals coming, for instance, from industrial machines, to look at if there are similarities, to analyze what is happening there, if it's in the way we want it to be or not. We use game theory to look at how is the equilibrium between the attacker and the defender. Are they equal? What does it mean if they're equal in their powers or if they are not? We look at vulnerability reports, so textual representations of security incidents that people are filing. We look at how can we automatically analyze them using so-called natural language processing to create something that the machine can process afterwards for doing all the magic that we do by protecting the system, detecting anomalies and so on. So to get that as support input, we look at software-defined networking, so internet parts or network parts where we can reconfigure the packet routing on the fly. Then we look at how can we ensure that the configurations are matching to what we want to have and how we can use it to countermeasures against attacks. We use the digital twins almost in everything, as I told you before, especially also for resilience evaluation. So how resilient, how well does the system behave even under an attack? We use different analytics methods like time series analysis, statistic tests. We share incident knowledge for federated activity, as I told you before. We have visualization, as I also told you before, and as you also see on the top. And we develop resilient control systems, so systems that are fault tolerant and that can automatically run countermeasures when there are attacks. So now you know a little bit about the topics. We'll dive deeper into it later, but before we do that, let's come to something super important when you are at a research team, and this is not only the topics but the people, because they are the ones you develop your creativity with, and I have the pleasure to work with lots of extraordinary people. Let's meet some of them.
Hassan Shaitu, PhD student. I was born in Beirut, Lebanon. I joined the Chaire cyber-cni in 2020.
Hello everyone, my name is Min. I joined the cyber-cni Chaire in April 2019.
Hello everyone, Raphaël Larsen, PhD student. I was born in Paris, France. I joined the cyber-cni Chaire in 2017.
Hi, Alexander Kabil, postdoc researcher. I was born in Paris. I joined the Chaire cyber-cni in 2016.
Hello, Edwin Bourget, postdoctoral researcher. I was born in Brest, in France. Chaire cyber-cni in 2016.
Dominique Pastor, professor. I was born in Cahors, France. I joined the Chaire cyber-cni in 2017.
Thomas Robert, associate professor from Telecom Paris. I was born in Bordeaux, France. I joined the cyber-cni Chaire 2017.
Hi, Jan Busnel, head of the Network System, Cybersecurity and Digital Law departments at the IMT Atlantic Rennes campus. Very proud to have this chair in the department.
And the pleasure is all mine, because it's really a pleasure being at that department, working with the teams there. So come over, visit, great. So from the people, let's come back a little bit to the research. Let's have a look at the domain. As example, I use now an industry example, so a production site. And when you looked at a production site in the earliest 20th century, this is how it looked like. What is characteristic for it? We have lots of people. We have machines that are doing some work. The machines are isolated. They're doing something. The humans are taking the products, going to the next machine, continuing to do something there. So isolated things, doing something with lots of humans. Actually, this is also similar to what you found at the beginning of the 21st century, because there the only change was that you introduced a little bit software, but besides that you had still a little bit similar processes, but of course things were a little bit more modern. And then came Industry 4.0, everything got networked. And let's walk over to a more networked facility now. So here you see a more modern production. An industrial robot is currently coming in. You see lots of compute devices. You see that there are not too many people. As said before, characteristic for that is that everything is interconnected and that you have processors and software processes that control the entire thing. Let's have a look at the setting. So we have our factory, we have the machinery, and on top of that we now have the embedded controllers of this machinery, and they're all internetworked, and then they create a setting where everything talks to everything. This is exactly the Industry 4.0. The internetworking does not end at the factory limits, but it goes into the cloud, it goes to the internet. And more recently, we also have something that is so-called edge fog, which is the cloud closer to the place where the compute power is needed. This is motivated by having lower latency. It doesn't take that long to get the info upwards. And from a security perspective, this is much better because the data is not in the big internet exposed to all the threats we have there, but it's closer to the factory. So typically we don't have only one factory, but we have multiple factories within a company and also across companies. They're all internetworked, and what is interesting to us right now is the attack potential. So if we would have isolated factories, the attackers would have to be insiders, like this one here. So they have to be your employees. If you have a good company culture, you might prevent them from attacking your factory, and in most companies this is working quite well. So we have a quite limited attack potential. Then when we come to the edge fog, this is more interesting because there's more data coming together, so therefore it's also more valuable to do attacks there. Also when you do sabotage in the fog, then you can affect multiple of the factories that are actually below. And when it comes to the cloud, then we have the full attack potential from the internet, because literally everyone connected to the internet can try to attack your systems. And you remember, for remote control, for instance, we want to have some functionality that people can use, and therefore we have attack potential even in the best security by design secured systems. So we definitely have to do something. Why do we have to do something? So what is the security risk? I put you 3 examples here. First one I just call security. So here, imagine you have a factory, someone is attacking it. What is your problem? Well, first of all, your machines might get destroyed, then your production might stop and you might lose millions of euros per day, for instance. So it's something that you obviously do not want. The second threat I want to look at is called safety. What is this about? This is about you have human workers and they collaborate with machines. So let's bring an industrial robot in, and so if this industrial robot does something it's not intended to, it definitely has enough power to harm you or even to kill you. And now imagine there's an attack ongoing and this industrial robot is getting misused by an attacker, then you're in big trouble. Therefore you have to provide security to your systems. And the last point, also super important, privacy. The systems we are looking at, they are so-called context sensitive. This means that they interact dynamically with the environment they are in. And as in the environment, they're also humans. They directly or indirectly collect data about these humans. And this data has to be protected. It has to be made sure that it's not available to purposes it was not intended to. Because if you lose your customer data, for instance, you can be sued for good reasons. And then you're in trouble also monetarily, but personally you have a strong interest for that, because when, for instance, everybody knows when you're at home, they can break in there. When everybody knows what you're eating, when you're at which place, with whom you're talking and so on, then you have a problem. And therefore privacy also super important. So now we know what are some of the problems, some examples for the problems. So what can we do? Well, We can do three things. We can first of all do the security by design. So we heard about it already. So securing the systems in the best way possible. But it's not enough because the systems are dynamic, so they have to be able to change, and therefore we have to adapt our defense mechanisms to that one as well. This is what we do with automated monitoring and defense. And on top of that, we always have to make sure that the human stays in the loop to have an overview, because humans can react in the end better if they have the right information, because they know the bigger context of the system that is not part of the system typically, and also because they have to bring in the configurations for the systems. Not surprisingly, all this matches to what we're doing, so the prevention is an important step. Implementing the security by design, you see on top that some of the attackers or some of the attack potential already vanished. Second point is the detection and also the defense, and third point is the defense and also the bringing the human in the loop, and ideally the entire attack potential is gone then. Let's get back to the people at the Chaire. So what are they at the moment working on?
Industrial systems.
Formalization of resilient systems.
Security risk optimization for learning on heterogeneous quality data.
The management of access control in IoT infrastructure.
Safety and security.
Threat analysis.
Diagnose incidents.
Enhance situational awareness of cyber analysts.
Random distortion testing, RDT in short.
Traceability and integrity of information.
Platforms for research purposes.
Values from sensors, actuators, and automata.
Detection of anomalies.
NFV, which is network function virtualization.
Critical systems.
Risk analysis methods based on extension of attack graphs.
Anomaly detection in physical data from the Secure Router Treatment Testbed SWAT.
Network intrusion detection system.
Access control policies on IoTs.
Machine learning to design ideas.
Yeah, so probably you found, if you're familiar with the cybersecurity topic a little bit, you found who's working on which topic at the moment. One thing that might be interesting for you is that at the moment we have some vacancies. So we're currently looking for postdocs, we're looking for PhD students. So if you're searching and you're an excellent researcher, please feel free to get in contact with us. The same applies, of course, if you are doing research and you think, wow, cool what they're doing. I would love to collaborate with them on doing some exciting research. We're always very happy when we hear from you. You see on top here our email address, hello cyber-cni.fr. Please reach out. We're happy to exchange. Okay, so let's come to the last part of our tour. So to do the research we do, we have wonderful facilities, and I will present to you some of them. So let's start at the top left here. So what you see there is a Fischer Technic, or actually multiple Fischer Technic factory emulators. These are miniaturized factories where you have all the processes like the conveyor belt here. The special thing about it is that they are controlled by actual industrial controllers. So we have the programmable logic controllers, the PLCs, that you also find in a real factory. The only difference is that we have the small factory where we can see everything, where we can control everything, and where we can do experimentation in a safe space. This is very exciting and very important. Here you see something similar, only that the processes that are controlled by the PLCs are not miniaturized factories with hardware, but just in software. Here you see a cream factory process where you can manipulate everything. And again, you have the real PLCs. That means we can emulate attacks by manipulating the values here and test our defense mechanisms and observe what is really happening there. So here you saw the PLCs at the moment. Then, of course, we also have servers where we can do simulations, but we also have an Airbus Cyber Range where we can do structured simulations of huge settings, which is also super helpful for doing research. We have some more hardware we can control. So this is a motor. This here is a real heating system where we have an actual water boiler and a radiator. We'll also see it in a second. This one here is an industrial controller where we can manipulate what it's currently doing and seeing. So here you see the water tank, for instance. Then we have the 3D interfaces that I was talking to you about before. And here you also see the radiator now. And then at the department, we also have great material that is there. We have 3D printing, laser cutting, and many more things that you find in the typical fab lab. And this is quite cool because with that we can do real prototyping of hardware. Okay, and last but not least, the campus. We have a wonderful campus with currently 3 research teams and lots of researchers who it's a pleasure to interact with. Currently on the way to our library where we have all the important books. Also the LaTeX book by Leslie Lamport, for instance. Et voila. So why could you be interested in doing research at the Chaire or with the Chaire? Let's listen again to the Chaire members.
The Chaire is an amazing opportunity to meet and work with many academic and industrial partners.
The diversity of the skills that can be found in the Chaire.
It's a great place to work and to provide innovative ideas.
We can easily have feedback from industrial partners and yet maintain our freedom in research.
So many people with so many different backgrounds and so many different positions.
As a PhD student, I want to focus on my research. So the Chaire provides me with all the requirements to do so in the best possible way.
The diversity of problems that are studied and the diversity of the solutions that are proposed.
Fuel for innovation and improvement of my research.
At the end, what is very nice is that because we have the same concern to cybersecurity, improves the system security or understand how new attacks can be designed, we can understand each other.
So here ends our tour. I hope you get an idea and we are looking forward to hearing from you.